Have you ever wondered how AI systems reason under uncertainty? Could you guess it involves a bit of probability theory and a lot of logic? It's all about the intriguing concept of conditional independence. This principle lets us break down complex probability distributions into smaller, digestible parts, making it easier to model and predict uncertainty in real-world situations. But the magic doesn't stop there, so stay tuned. In the next few minutes, we'll uncover the mystery behind this fascinating concept. Now, diving into the world of conditional independence may seem intimidating, but let's break it down. Imagine you're trying to predict tomorrow's weather. You know that the weather depends on a lot of factors, like humidity, wind speed, temperature, and even the weather of the past few days. Now, if you were to consider all these variables together, you'd end up with a tremendously complex model. But here's where conditional independence comes in. It allows us to say that, given today's weather, tomorrow's weather is independent of the weather from 2 days ago. This significantly simplifies our model and makes our prediction task much more manageable. Another example can be seen in the medical field. Say a patient has a cough. This could be due to a cold, flu, or something more serious like pneumonia. Now, if we know that the patient has a cold, the probability of them having pneumonia, given they have a cold, becomes independent of other symptoms like a cough. This simplification helps doctors make more accurate diagnoses. So, conditional independence is a way to tame the complexity of the world around us. It's a way to simplify the intricate web of dependencies that exist between different variables, making our models more manageable and our predictions more accurate. So, in a nutshell, conditional independence allows us to simplify complex problems by breaking them down into smaller parts. Now that we know what conditional independence is, let's talk about its role in AI, specifically in representation. You see, representation in AI is all about how we structure and store information within an AI system. It's like the blueprint of a building, defining how the rooms connect and where the furniture goes. In our case, the rooms are the variables and the furniture is the data. Now imagine trying to map out a blueprint for a complex building, say a skyscraper. It would be a nightmare, right? But what if we could break it down floor by floor, or even room by room? That's where conditional independence comes into play. It allows us to simplify these complex structures into smaller, more manageable parts. This is crucial when dealing with real-world problems where uncertainty is the norm, not the exception. By breaking down the complexity, we can model and reason about uncertainty more efficiently. Different AI techniques approach this in various ways. Bayesian networks, for instance, use a graph-based representation to model the probabilistic relationships between variables. Markov networks, on the other hand, use a mathematical structure to depict the dependencies between variables. And then we have influence diagrams, which combine decision theory and graph theory to model decision-making processes under uncertainty. So, the way knowledge is structured and stored in an AI system is crucial for its ability to reason under uncertainty. We've learned quite a bit today, haven't we? Let's wrap it up. We delved into the fascinating world of artificial intelligence, exploring the role of conditional independence in reasoning under uncertainty. This is a concept in probability theory and statistics that allows AI systems to break down complex probability distributions into smaller, more manageable parts. We discovered that conditional independence is not just about simplifying these distributions, it's about making it possible for AI to tackle real-world problems that are fraught with uncertainty. In these scenarios, conditional independence proves to be a powerful tool, allowing AI systems to model and reason about uncertainty effectively. Then we moved on to the role of representation in AI. We saw how different AI techniques like Bayesian networks, Markov networks, and influence diagrams use various representations to model conditional independence. These representations determine how efficiently an AI system can reason about uncertainty. It's all about how knowledge or information is structured and stored within an AI system. In essence, the power of AI lies in its ability to reason under uncertainty, and this power is largely derived from the concept of conditional independence. This understanding is fundamental for those who aim to build robust and efficient AI systems. Now you know how AI systems reason under uncertainty, and it all comes down to the simple yet powerful concept of conditional independence. The next time you marvel at the workings of an AI system, remember this vital cog in the machinery.